So we have 1.44, everything else. So then we need to go ahead and do the addition now. And like I was saying, you don't have to clear out your calculator, but we just need to kind of mentally note what we should have. So plus 15.37. And then how many sig figs should this number have? So I'm writing out, that's what my calculator had, was the 16.81. What do you guys think? So what rule are we applying here? Decimal places, right? We're doing the addition rule now, decimal places. So watch out when the operation changes, because which rule you apply changes. So here we should have 3 significant figures. So if you're afraid to speak up for the sake of you're afraid to be wrong, you are more than welcome to hold your fingers up, that kind of thing. That's to show that you guys are kind of paying attention. All right, and then let me go ahead and divide. Oops. Divide, and I should have, let me just do it for the sake of discussion here. Let's write 3.14. You have a question? Okay. All right, so I went ahead and divided there, so I get 5.35, etc. So how many sig figs should I report my final answer to? 3. Do you guys remember how many sig figs should be in pi? So I did type in 3.14, but is that how many sig figs are in pi? No. What do you guys think? How many sig figs are in pi? There's infinite. That is an exact number. And I think it's kind of interesting that, pi is irrational, and it's because the definition of pi does not fit well into a base 10 number system. If it were a pi-based number system, it would make perfect sense, right? And you have to go over that kind of stuff in trig. But the point is if you have to use it in a calculation, if you do punch in the 3.14 in your calculator, that's not a limiting factor on the sig figs. So you need to be careful on what you're limiting your sig figs with. All right. So with that in mind, I do want to go ahead and continue.
You wouldn't have the 3 after 0.25.
That's the limiting thing here. 3 sig figs we came in with. Mm-hmm. So we get 3 sig figs at the end because we're following the multiplication rule now. So the first step here, you were just summarizing the whole problem again. We did the multiplication rule when we did the square term here. And that left us with 1.4 and 1 decimal place. Addition rule, get 1 decimal place. And then the last step here, we're doing a division, so we use the multiplication division rule, and we get 3 sig figs at the end.
That has 4 digits in total, but it's only 3 significant figures in that one.
Yeah, so this is what we came in with.
Okay.
But only if we were to end the calculation here, only 3 would have been significant. So the whole point of doing this is that you don't want to round early. So you don't want to fully apply the rule like by dropping things off yet until the very end. Because if you were to round each step of the way, your answer would be a little bit different than what I have here. And when the way that the online homework as well as my self-grade, we base it off of rounding at the end. So you need to keep track of your sig figs as you go along. Thankfully, most of the time we're going to be following the multiplication and division rule. But we have to, illustrate the addition rule. It does come up sometimes. And you need to know when to apply which rule. All right. Good discussion about that. Let's go ahead and continue. So we're basically going to be working in the metric system in this class. So metric or SI system. So did you guys, I believe there's a discussion online, isn't there, about metric? Was that my 105 class who did that? I can't remember. Anyway, does anybody have know how many countries in the world use the English system of measurement? There are 3 countries. And one of them is the United States of America, unfortunately. And there has been some discussion about whether or not we should switch over to metric. From my understanding, it actually has been brought in front of Congress a couple times, And some people think the main reason why we don't switch is due to stubbornness. But I think the more likely reason why people are resistant is the cost it would take to switch. Because you imagine that nationwide we have how many road signs? And they're all in miles, right? So you can imagine changing every sign everywhere in the U.S. How much would that cost? Probably in the billions, maybe. It would be pretty expensive. So to keep things normal, we just stay in English. Just keep in mind, though, that when you're dealing with any kind of numbers in science, we're typically going to work in metric. There is some overlap between them. So the main units that we're going to have to deal with are units for length. And what do we typically use for length in metric? Meters. The centimeter or meter for the. Let's just look at the base units. So meter, and that's symbolized as m. And then some other basic units will be mass. And what do you guys think? Should be grams. And that's in G. And let's go ahead and make a list of the English equivalent over here. Let me fix the zoom on this a little bit. All right, and bring this down. There we go. Come on. All right. So some equivalents that we would see in the English system would be something like the foot, and then gram would be probably something like the pound. So if someone were to, you're reporting your weight and suppose you're really self-conscious about your weight, would you rather report it in grams or pounds? Do you think? Probably in pounds, because you would seem even if you're really skinny and really lightweight, you would seem to be really overweight if you wrote it in grams until you get kind of an idea of the context of it. So if you want to figure out how much you weigh in grams, roughly multiply your weight by 453, and that gives you an idea of how much you weigh in grams. That's a really small amount, right? So part of this class also is getting kind of a physical sense of how big these numbers are. All right, so length, mass. And then we have things like temperature. And you guys know what for metric what we use? Kelvin. There is Kelvin and there was one other one. We actually have two. Celsius. So we have Celsius, which is degree C. And we also have Kelvin. And I want to point, we're going to go over Kelvin a little bit today if we get time. We should have time. But I want to point out here that there's no degree symbol in the Kelvin. It's just the letter K, and it's capital. And then we also have the one for the English system, which is the Fahrenheit. Fahrenheit. That's how you remember how to spell it. And that is degree F. All right. These are the main ones that we're going to have to worry about. All the other units that we're going to work with in this class are derivatives of these. So, for example, if we were to say, do you guys know what we'd have if you were to take a length and square it? What is that equal to? What's that? Well, we're not looking at specific units. We're just looking at what are we actually measuring here. So if you were to take the length and square it, what are you actually looking at? Area. We're looking at area. Yep. So most of the units we're going to work with are combinations of these ones. So we have area, which is a length squared. So when you have a unit, if you see it has a distance and it's squared, that's telling you you're looking at an area. And then the other one, what if we were to cube it? So a length and raised to the third power. Okay, no. What's that? Volume. That's volume. Yeah, volume. So these are where your liters, milliliters, gallons, all that. If you break it down to its core, it's actually a length cubed. And commonly in chemistry, we're going to use a centimeter cubed. And we know a centimeter as being a distance. But if we cube it, we're looking at basically a three-dimensional object now, and that is the volume. And we have a little bit of this stuff later, but do you guys know what a mass over volume is?
Density.
Yep, that is density. And that's actually the end part of this chapter is about density and how we use it for conversions. All right, and these are the main ones I think we're going to work with. I think another one we had is force per area. That's pressure. But we'll see that stuff later on in chapter 12, I believe it was. All right, so let's take a look at the metric system itself. The convenient thing about the metric system is that it's all base 10. So if you're going back and forth along metric, it's actually pretty straightforward. And typically, this graph is actually from your book. I believe it's on page 28. Don't quote me on this. I had the version of the book from last semester, and I just changed it this semester, and I didn't bother getting a new one because it's the same book. So in chapter 2, you should have this table. And have you guys covered this in a previous class? Like in probably your high school math courses or a physics course. Who's learned metric before? Yes, just raise your hand if you've learned metric before. So most people have. So I do want you guys to unfortunately memorize a particular range. And I want you guys to know the kilo to the nano. You should know how to work with the other ones, but these are the ones that I want you guys to know off the top of your heads. So if you're afraid that you haven't committed these to memory by the time the quiz rolls around, you now have something to put on your note card, right? So, okay, so I want to briefly explain here how this chart is read, because it might be a little confusing on which form of the number that you want to use. So let me zoom in a tad. All right. So these multipliers here are always in reference to the base unit. So basically these multipliers are a way to express really large or really small measurements. So these are basically your numbers, and then if you don't tack a unit onto it, these numbers are meaningless. So in general, numbers are meaningless without units. So for example here, if we say that we have 10 grams, you could also say that you have a decigram. Sorry, a decagram. Deci is below. Actually, we don't need these ones either. We don't use those all that much. So let me cross that out to make it a little bit straightforward for you guys. Let's memorize the ones that are actually used a lot, if we're going to spend time memorizing things. All right, so if I say that I have 1,000 kilograms, is that equal to 1 gram? Is the way that table is being read. So right here it says kilo equal 1,000. So the question I have for you guys is it saying 1,000 kilograms is a gram, or is it 1,000 grams is 1 kilogram? Yeah, so this is the amount of the base unit that you have. So if it's saying here that you have 1,000, that means you have 1,000 of the base unit is equal to one of these. And then the reverse case here, when you're going below 0, if you're saying here that you have 0.01 meter, that's 1 centimeter, or the other way to say it is that you have 100 centimeters per 1 meter. And I want you to be comfortable with recognizing either way for that. And let's go ahead and start off with the little conversion problem and how we do conversions. So what if we have, let's say, 17.5 kilograms, and I want to convert that to grams. The general way you want to approach these conversion problems class with like ratios or something, you want to try to avoid using a ratio system as much as what I'm going to show you here. I like to do a string of calculations versus a ratio. The ratios do work, but you have to just do one at a time. And a lot of these calculations are multi-step. Anyway, to the point at hand. So here we take what you're given. You're then going to take a conversion factor. So conversion factor. This is your table information. You want to put the desired unit on top and then the given unit on the bottom. That way, when you multiply this out, the given units canceled and leave us with the desired. All right, so that in mind, we can go ahead and take the original problem, the 17.5 kg. The conversion factor that I need here is I want kilograms to cancel and give me grams at the end. So now we plug in the definitions here. There are two ways to do this, and I want to go ahead and show you both ways so you're comfortable seeing it either way. So no matter which way you do it, you're going to have grams on top, kilogram on the bottom. But one way of reading that table was if you had 1,000 grams. So we're going to write it as 10 to the 3 over 1 kilogram. We also know that if you go the other way here, 1 gram, and what do you guys think I should put here for the number? So I want to put it as a 10 to the something. What do you guys think? Is it to the third? 10 to the minus 3. Yep, 10 to the minus 3. So what I did here is I used the inverse property to do that. And the reason why you want to be comfortable either way here is because if you don't remember these definitions, if you're given them on a test, you want to be able to use them comfortably either way that they're presented to you. And you also may notice here that I'll just write a little note here on the side that 1 over 10 to the minus 3 is equal to 10 to the 3. So mathematically, you're doing the same thing. So you're not really changing anything here. Let me zoom out. Here we go. And the reason why I want you guys to write things this way rather than writing in 1,000 is because we're basically working in powers of 10 here. So we could do this calculation without a calculator, right? So we have, if you were to put that in scientific notation, how would you write it? This number right here. It would be, what, 1.75 times 10 to the 1 or 2? 1. Yep. So then when you're doing the math here, it's 1.75 times 10 to the 1 times 10 to the 3. So what does that equal to? 10 to the what? 10 to the 4. Yep. We learned that property last time where if you're multiplying them, we just add the exponents together. So that way you can do this calculation without a calculator. And I'm hoping we'll eventually get to the point where we can do this kind of thing in our head. And I'm really hoping you are by the time you're in Chemistry 121, that you don't need to do this calculation out every time. Don't forget your units, because numbers are meaningless without a unit. So it's grams. And I'm actually really particular about that. Make sure you include your units. And this will work out to be the same over here. So 1.75 times 10 to the 4. And if you're not convinced, you could go ahead and punch this into your calculator, and it should give you the same answer. What's that? Oh, sorry. Let me fix the camera. There. And units, grams. And that's a little side note there. Actually, let me do this. Let me angle this up a little. All right. Any questions about this? right, do we need to do, I think maybe one more, and we'll be a little quicker about it. And then I'm going to show you guys the trick. But no questions, let's go ahead and move on. All right, so what if we're going and go ahead and do, let's say, 2.57 times 10 to the minus 3. And let's go ahead and say this is liters. And I want to convert that to milliliters. So we go ahead and take what we're given. So 2.57 times 10 to the minus 3 liters. And we need a definition. And we need to figure out where units go. We do have a conversion to go from liters to milliliters. And I like to work with positive exponents. So I need to plug in a factor of 10 to the 3 somewhere. Should I put it on the top or the bottom? Top. Yep. And I know that by looking at the table, if you've forgotten. The milli is the thousandths. So it means we need 1,000 of them to be 1 liter. And like I said, I like to work with positive exponents. You don't have to work with positive exponents. I think it personally makes it easier. So what do you guys think the answer to this is? We have 2.57 times 10 to the minus 3 times 10 to the positive 3. Yep, it's 2.57. So we have 10 to the 0, which is 10 to the 1. Or sorry, 10 to the 0, which is just 1. So this effectively cancels out, and we are left with 2.57 ml. And I apologize if it feels like if you think I'm overcomplicating it by adding these exponent tricks, but the whole idea that I want you guys to be able to do this without a calculator. So if you want to become good at metric, do them without a calculator.
Is it any reason that the L is capitalized like this?
That's how the unit per liter is written. It's a capital L. Yep. It's technically incorrect, but I don't mark off for it or anything, but it's technically incorrect. Go ahead.
So we were working with like negative exponents with the whole answer to negative.
No. So let me try the version with negative exponents, and I will go ahead and do it in my calculator, just so we're clear. So if we use the negative exponents, that would read, basically what I mean by that is here for the lead, this is the liter value, so that's 10 to the minus 3. So that would go here. Over 1. And I don't think we really need a calculator here. We can see that 10 to the minus 3 and 10 to the minus 3 cancel out. So that leaves us with the 2.57 again.
Oh, so they cancel out because they're exponents and you add the exponents.
Yeah, so we have the same thing divided by itself here. So the liters cancel out, and then the 10 to the minus 3 cancel out as well.
In my head, I was like thinking multiplication, but that's not.
All right, let's go ahead and do a few more practice so we're sure. One case that you might have to do is you might have to go from a unit that's higher than the base unit to one that's lower than the base unit. And there's 2 ways to do that. One is you can do it in either 2 steps or you can do it in 1 step. And I'm going to show you both ways. You need to understand how to do it in multi-steps before you can do it in 1 step, though. So what I mean by this is suppose we were going from, let me just make up some number here. So 4.32 times 10 to the 12. And let's say we're working with nanometers. And I want to convert this to kilometers or kilometer. So you may notice here we don't actually have a direct conversion, but we do know a few things. We can compare both of them to the meter. So in this case, we don't have a direct path. You can go ahead and do it multi-step by first going from nanometer to meter. We have that conversion, and then we also have the conversion from meters to kilometer. So here we have a pathway. If you're doing this type of method, every single arrow is a conversion factor. So we have 2 conversion factors that we need to use here. All right, so 4.32 times 10 to the 12 nm. So the first conversion that we're going to use to go from nanometer to meter. So 2 things you want to think about is we're going to have a 1 in there and then a number that's not 1. And I like to work with positive exponents. So what number should that be and where should I put it? So numbers probably going to go in the bottom. And what is the value? 10 to... So I'm going to put the 10 here. Is it positive 9 or negative 9? All right, so this is how many meters are in 1 nanometer. So that means you need 10 to the positive 9 of those to be 1 meter. The other way would be 10 to the minus 9 meter per 1 nanometer. So if we're using the table directly, that's how you would write it. But like I said, I prefer to work with positive exponents just to make things simple in the calculations. Does it make sense how we're getting this 10 to the positive 9?
Yes.
Okay. We're going to see it's going to look a little bit different when we go from meter to kilometer. So now I want to put 10 to the positive exponent. Where do I put that number? The bottom. And what is the power on it? 3. Yeah. So without a calculator, we can now do this. We have effectively 10 to the 12 divided by 10 to the 9 divided by 10 to the 3.
Is that table not in the e-text version?
It should be in the e-text, yeah. Yeah, it should be about, I'd say about halfway through chapter 2, after all the sig fig stuff. It's right after that. Yeah, it says Pearson e-text 2.0. Yeah. What do you guys think? What did that equal to? Without a calculator. It's equal to 1. Yep, so we have 10 to the 12 over 10 to the 9. The bottom here is 10 to the 12 effectively. So we have 10 to the 12 over 10 to the 12. So let me go ahead and write it out just so we're clear about what's happening here. So this all reduces to 10 to the 12. And that all just cancels out. So it's similar to what we had earlier, where we have 4.32 times, if we're worried about scientific notation, it would be 10 to the 0 km. And unless I'm specifying scientific notation, you can go ahead and write it like that. So another one question here before we move on is, okay, here I have 3 sig figs, and then here I only had 2 and then 1. Like, why didn't I reduce down to 2 or 1 on the sig figs? What's that? Yep, the given is what you're is deciding here. So it's always like what you're physically measuring is what's going to limit your sig figs. So these are all definitions. Those are exact numbers. Those are your table information. So don't forget that anytime you use a conversion factor, these are not going to limit your sig figs. And the way it works out with the multiplication rule is that whatever you're coming in with, that's how many digits your answer should have as well. The only time that's different is when you're doing a conversion that does require a addition and subtraction. We will see that today. And that's mostly with the temperature conversion you see that. The shortcut I wanted to show you guys is here on the chart. So we went from kilo to nano, right? So we saw that it was, for nanometer, it was 10 to the 9 of those. And these are 10 to the minus 9 versus 10 to the 3. And the difference between those, it's not really showing up very well, but bring it up closer to the camera. 10 to the minus 9, 10 to the minus 3. What is the distance between those? It's 10 to the 12. They're fully 10 to the 12 away. So basically, how far is 3 and negative 9? They're 12 apart from each other. So what you could have done instead, that would have gave you the same answer, is you could have said that it is 10 to the 12 nanometers per 1 kilometer. So this is when you guys get really good at this. So when you're practicing it, first practice it. If you're understanding this way, go ahead and try it this way, and that's going to save you time. Remember, time saving is crucial on doing well in this class. Okay. Any questions about that before we move on? All right, so next thing I want to show you guys, it's actually on the same page here for the conversions. So I'm betting if you live in the UK, they probably don't teach this part in this class, but we have to here. And it's how do we go between English and metric? So you're going to have to do that. So it's actually on the same page, at least in the version of textbook I had. It should be on the same page in yours. And how to go between different English and metric units. You do have a more comprehensive list if you want to go ahead and just look it up online. They're pretty easy to find everywhere on the internet. I will provide anything like this. So because they're not factors of 10, they're not very easy to memorize. And I will always provide an English to metric conversion. Never write that on your note card. You're just wasting space. Some of them, though, you will come to memorize over time. And that's just a matter of practice. And that's awesome if you do. Doesn't really matter if you don't, because you will always be provided with it. And that is also true on standardized tests and whatnot that we give in later chems. All right, so the conversion I want to go ahead and try here is, suppose we were going from, let's say, 17.893 centimeters, and I want to convert that to inches. And the conversion factor that's given here, it's a little bit different than the one that I remember, but they're all kind of working here anyway. Oh, they do have it on here. It is 2.54 centimeters is equal to 1 inch. So when we use these conversion factors, we need to make sure that we're plugging in the 1 in the correct spot and the 2.54 in the correct spot. So try not to get these mixed up. The approach is identical as the previous problem. So I want centimeters to cancel. That way, when I multiply these out, centimeters drop out, leave us with inches. And where do I put the 2.54? Top or bottom? Bottom. Yep, 2.54 per 1 inch. All right, so, 17.893 divided by 2.54, and I get this long number here, 7.0, blah, blah, blah. How many sig figs should I write my answer to? 5. Yep. So even though that number has 3, that's a definition. It's what you came in with. So to 5 sig figs, it looks like we should be rounding up, like so. Yep, because it was like 7.044488, etc. But the cutoff is the last 4, round up, because we're dropping the 8. Not quite done. You must include units. They don't mean, numbers mean nothing without a unit. All right, so let's go ahead and do the reverse case now, and then I'll show you some other types of conversions. So in the reverse case, suppose we had, let's go with 75.8. That works. And I want to convert this, that's inches. Actually, let me go to a different unit here. Let's go to the meter. So this one, we don't, we're going to pretend that we don't have the direct conversion. I do believe this is on here, though. Let's pretend we don't have it. And the only one that we have to work with is this one. We can still do this. So basically, we have to go to a point that we can use. We can go from inches to centimeter. And then we also know how to go from centimeters to meter. So it looks like we're going to do a two-step conversion here. So 75.8 inches. And now we need to start plugging in units where they belong. So the first conversion is going to go from inches to cm. And then since we're going in the opposite direction, we need to put the 2.54 on the top and then the 1 on the bottom. And then here I want to go centimeters to meters. And we like to check our units here. Inches we're going to cancel. Centimeter we're going to cancel. We're going to be left with meter at the very end. All right, so I want to put a 10 to the 2 in there somewhere. Where do I put it? Top or bottom? Bottom. Yep, it's 10 to the 2 centimeter per 1 meter. All right, so here, this math is not as straightforward. This is the time when I want to use a calculator. I mean, yeah, you could technically do it by hand, but that's going to be a time sink. So think about what takes longer, doing it by hand or doing it with the calculator. And then when you're doing the base 10 stuff, I think it's actually slower to use the calculator than it is to do it in your head. All right, so final answer there, I get 1.92, etc. So to 3 sig figs, 1.93 meters. All right. It all makes sense? Pretty straightforward? A lot of practice. So we actually have worksheets. I believe it's activity 1.1 and 1.2 have conversions on there that you want to work through. And it had a mixture of metric to metric, and then we also do some English to metric. You could do English to English as well, but I believe it's in the homework, but it's the same approach. And remember that if you're working within metric, that you want to get in the habit of doing the metric conversion without a calculator. It'll make you so much faster at this. And you'll understand physically what's going on a little bit better too, I think. All right. So another type of conversion we have here is, remember earlier I was talking about we have these different types of units that are derived from the other ones. We have the things like the area was a length squared, and then we had the volume was a length cubed. The issue is that if you're using a conversion that is not raised to a power, you have to raise the conversion to a power when converting those units. So I want to go ahead and do an example here. So suppose we were going from, let's see if they have one here. They don't have inches cubed in here. Times 10 to the 6th. And let's say this is inches cubed. And I want to convert this to centimeter cubed. And the kind of conversion factor you're going to be given is the same one that we had earlier, which was the 1 inch is equal to 2.54 centimeter. All right. So it looks like we have a direct conversion. We're just going to go from inches cubed directly to centimeter cubed in one step. The notable difference here is that we need to make sure that we do it in such a way where the units cancel properly. So the conversion here is inches to centimeter. And then you're plugging your numbers in. It is 2.54 centimeter per 1 inch. And notice here, if we were to start canceling units, the inches would not fully cancel. You'd actually end up with inches squared times centimeter cubed. So in order to make sure that everything's canceling, you need to cube the whole thing. So cube the whole term, and that cube term applies to everything on the inside. So I'm going to go ahead and write them in there for the sake of discussion. The 2.54 gets cubed. That's the crucial thing that you need to cube in your calculator. The units get cubed, all the numbers. So when I punch this number into my calculator, I need to make sure I punch in 2.54 to the third power, not just 2.54. All right, so pretty straightforward here after you figure that out. So 3.589 times 10 raised to the 6th power, that was the number we started with, times 2.54, raise that to the 3rd power, and I get that long number. So we get to 4 sig figs. What was that? 5.8813. And it's 10 to the what? What's that? 7? Let me double check that. So it's 2, 3, yep, it's 10 to the 7. That's positive 7. All right. And units, don't forget the units. Centimeter cubed. Another thing we're going to see in this chapter as well, does anybody know how many milliliters are in a centimeter cubed offhand? How many milliliters are in a centimeter cubed? What was that? I heard something. They're actually equivalent. So 1 centimeter cubed is equal to 1 ml. So you're going to see a lot of problems in this chapter as you're doing your practice. They're going to be asking you to calculate milliliters, but it'll be logical sense to go to a centimeter cubed in your conversion process. So after you get there, we can just say, okay, they're equal. So I could, at this point, report my answer as milliliters instead. So I could report it as ml because of the fact that these are equivalent, or ml. All right, let's go ahead and do a conversion that requires a few steps.
Is it like no volumetric numbers?
What's that? With the equivalency here? No. We use, I mentioned, or it turns out that water is used as a base for a lot of different things for measurement within science. And it works out that if you have exactly 1 milliliter of water, that's if you have a cube of it, it's a centimeter cube. And then that's also equal to 1 gram. So we use like 1 gram, if 1 centimeter cubed is 1 milliliter. And then we're going to see, we'll be starting this next here, temperature conversions. The 0 and 100 marks in the Celsius scale are based off of water. All right, we'll come back to this stuff, but you guys have plenty to chew on with the conversions over the weekend. I am going to jump ahead a little bit into chapter 3, just a tad. I wanted to show you guys how to do temperature conversions today. And then what we'll do next week, we'll start with density. If you guys want to practice work ahead over the weekend, you could look up density and how to do those kind of problems, but we'll actually cover them next week in class. So for now, I want to just go ahead and take a look at temperature conversions. Right, in 1 sec, I want to grab a ruler. Okay, so we talked earlier about the different temperature scales that we have. We saw that we have 3. So I'm going to go ahead and draw 3 lines, and then we're going to make some comparisons between them. All right, so we have, let's go ahead and say the first one is Kelvin. The next one is degree C. And this one here is degree F. All right, so the few points of interest that we have one for the freezing point of water. And the next one here is the boiling point of water. This is actually how we defined the temperature scales for Celsius. So it turns out that it is 0 degrees. Let me write this in, let's use green. So here is the freezing temperature, and that is at 0 degrees C. And this one here is the boiling temperature. And let's see how much background knowledge, if anybody has this in this class, is. Did anybody know why we measure these points at sea level?
Because if there's more pressure, it should change.
Yep, so the actual pressure changes as we go above and below sea level, so that'll actually have an effect on the freezing and melting points and boiling points. So we have to measure them at sea level. All right, does anybody know the corresponding temperature in Fahrenheit for freezing? Like when they say it's below freezing outside, how cold is it? Below 32, right? So 32 degrees is freezing. Some misconceptions or mistakes I've seen people make is some people think that if below freezing is below 0. They are completely different. If you've ever been in below 0 weather, you know, because below 0 is freaking cold. But 32 is not so bad as long as you have a jacket on. And it's not windy. Do you guys know what the boiling point is for in Fahrenheit for water? Yes, 212. All right, so we have 212 here. And degree F. And we'll talk about Kelvin here in a minute. So the next thing, so we have 2 different things here. One is the 0 mark or the freezing mark. Basically, that's the reference point that we're using in Celsius. It's not quite at 0 in Fahrenheit. So we're going to have to account for that offset in the calculation. So we have a 32. And the other thing that comes from the equation is how far of a distance they climb in the same amount of actual temperature change. So here the climb was, so the change, so we use that symbol in chemistry, the triangle. So the change in temperature here is 100 degrees C. And then what's the change here? Looks like 180 is the difference. Okay, so I want to go ahead and derive an equation from this information. So suppose you were going from, let's say, you wanted to figure out what degree F was if you were given a degree C. So we were given a degree C. So this is going to be the number that you plug into it. So I'm going to put a little box there. That's the number you plug in. The change is basically 180 degrees C. Oh, sorry, that's degree F there. That's a mistake. Let me back up just a little bit. That should be degree F right here. All right, so the difference here is 180 degree F per 100 degree C. I want degree C's to cancel, so I need to put that on the bottom, and they actually simplify down to 9 over 5. But I want to go ahead and include my units here just so we're being thorough. So it's 9 degree F per 9 degrees C. That means that as you go up 5 degrees Celsius, you went up 9 degrees Fahrenheit. So that's where that factor of 9/5, you may remember learning that from your other classes. And sometimes people have you learn it as 1.8. It's just how fast they climb in difference. And then right here, we have to compensate for the offset. They are offset by 32 degrees, because if you look at here, 0 degrees is equal to 32 degrees Fahrenheit. So we have to account for the offset here. And then if you notice here, I'm not going to cancel it out here, but I just want to point out that degree C's will cancel. And then we have degree F plus degree F. Your final answer will be degree F. Okay, we could do the same kind of logic to get to the other one, or you could do a little bit of algebra. I want you guys to understand the logic.
What's this square for you?
What's that?
What's that square there for?
Squared. Oh, that's where you put your number. Sorry, that's where your number goes. So it could be a blank line, whatever. That's where you plug in your number. Okay, similarly for going from Fahrenheit to degree C, the first thing you need to do in that case is account for the offset, then you account for the different rates. So what I mean by that is you need to subtract 32 first, and then do the multiplication. So this is going to work out to be 5 degree C over 9 degree F. And then multiply that. And this is where you're going to plug in your number. Make sure it's a little bit more clear this time. And this is going to be a number that's in degree F minus 32 degree F. In this case, the degree F's are going to cancel, and then we're left with degree C. Going between Kelvin and Celsius is a lot more straightforward because of the fact that they climb at the same rate. So we don't have this difference in how fast they climb, but they do have an offset. So we have to only account for the offset when going between Kelvin and Celsius. So let's go ahead and just back up here a tad. Does anybody happen to know what the freezing point of water is in Kelvin? Like 273.15. Kelvin?
Does Kelvin go for absolute 0?
We do have an absolute 0, yeah. I'm going to talk about that in a moment. We have here now, what's this brand new pen? 373.15 Kelvin. So notice how the difference there is also 100. We don't use the degree symbol there, we just say 100 Kelvin. Okay, so to go between Celsius and Kelvin, you just need to subtract the number. So right now, if I said it was, so right now it's probably about maybe mid-20s in Celsius right now outside. If you wanted to get to Kelvin, you just add the 273 to it. And then if you're given the amount of Kelvin, you just subtract off that number to get to Celsius. All right. The reason why this is important is because it gives us an absolute scale, and it avoids any complications you might have in the math by having a negative temperature. So it turns out that the coldest possible temperature, by the way that we define temperature, is absolute 0 Kelvin. And does anybody know like why that's the coldest temperature by chance? Go ahead. Yes. So technically the way that, and we'll go over this more detailed next time, but the way we define temperature is by how fast molecules are moving. And by that definition, the coldest possible temperature is when nothing is moving at all. And we, by the way that we understand the physics behind how atoms work, that's physically impossible. And that's useful because we're going to see in this class, we're going to have calculations where we have to use temperature in the bottom of a calculation, division. And if you have 0 there, what happens? It's undefined. It's infinity. So to avoid that complication, we work in Kelvin. So For the most part, we're going to work with Celsius in this class, but there is one chapter where we have to work in Kelvin, and that's the gas law chapter. But let's go ahead and get this equation up here. So if you're going from, if you want to figure out what Kelvin you have, you take whatever your degree C is, and you add 273.15. And then if you want to figure out what your degree C is, you take whatever your Kelvin is and subtract 273.15. So what is absolute zero in Celsius? Yep. And then for fun, you could figure out how cold that is in Fahrenheit. It's like negative 400 something. So when you think of like super cold outside, remember it could be colder, right? I think the coldest temperature we've gotten to is, I think it's 3 Kelvin is how the lowest we've gotten, and that's actually roughly the boiling point of helium. So it doesn't take very much to get helium to turn into a gas. All right. So what I want to go ahead and do, we have a few more minutes left in class, is I want to do some temperature conversions, and I want to make sure that we're applying our sig fig rules. And no groaning about it. This is like where it gets tricky is with the temperature conversions. All right, so let me check my phone real quick, and we're going to do some conversions with this number I get. So right now outside, I'm trying to get rid of my little calendar or my thermometer. So what is like this morning? Like what? Like low or high 70s this morning, something like that. 78. So let's say it was 78.5 degree F, and we do not actually have a direct conversion to Kelvin. We have to go to Celsius first. So I want to show you guys how to do that calculation, and then for practice, we'll go to Kelvin. Okay, so now we need to decide which form of the equation we're going to use. So I gave you 2 different versions. One was 9 over 5. The other one was 5 over 9. Which one do we use? We're going to be using this one. Because we want to figure out what degree C is. We were given degree F, and that's what number we're going to plug in. So that's important because you need to account for the offset first. So we're going to have 5 over 9. I'm going to drop the units off that now for the sake of simplicity. And we have 78.5 minus 32. Right, do we need a calculator for that yet? What is that equal to? Yep. So if we're talking about sig figs here, how many sig figs should that number have? If we're going to stop here. It's 3. Yep. So so we are doing an operation here. We're doing a subtraction, and that rule states number of decimal places. And how many decimal places does this 32 have? Has an infinite. It's an exact number. So that's exactly 32. So we have 1 decimal place, 1 decimal place. And the next portion here, this is probably where you want to use a calculator because it's actually a lot faster to use a calculator here than to do it by hand. But if you're really good with arithmetic like that, feel free to do it because that's up to you. I'm good at some of it. 46.5 times 5 over 9. And I'm getting 25.8, etc. So how many sig figs should my answer have? 3. Yes. And then here I'm going to put my unit back on there. So 25.8. And I'm going to not clear my calculator yet. So I'm going to leave that number in my calculator, but I'm going to report this answer as 25.8 degrees C. The way I personally remember which equation to use is that Fahrenheit is typically higher than Celsius is. So if you're trying to calculate Fahrenheit, use the one that has the larger number on top. That's the 9/5. If you're trying to figure out what Celsius is from Fahrenheit, Celsius is typically smaller, use the 5/9 version. So whichever one you're more comfortable with. All right. So next portion here is I need to go figure out Kelvin. And do I add or subtract that number? We're going to add it. So we're going to take our 25.8 and we're going to add 273.15. So without clearing my calculator from earlier, I'm just going to say plus 273.15. And I'm getting 298.98, etc. So how many sig figs should my answer have? Should be 4. Because we're adding here. Yeah, we're coming in with 1 decimal place. Need to end with 1 decimal place. So I'm going to report my answer as, that's going to be 298.9, I'm going to round up, so 299.0. So 299.0. Once again, what happened here is we are now applying the addition rule. We have 1 decimal place, so we get 1 decimal place in our answer. And because we went up in order of magnitude, we gained a sig fig. So be careful of that. If you're going up or down in order of magnitude, you're going to gain or lose sig figs accordingly. All right, I want to go ahead and do one more conversion just for the sake of discussion here. So I want to go the other way now. I want to go from Kelvin. What's that? Was there a question? Okay, all right. Oh, don't forget, remember, numbers are meaningless, not units. Breaking my own rules here. Don't forget your Kelvin. All right, so I did mention earlier about converting 0 Kelvin to Fahrenheit. So let's go ahead and do that, and we'll see exactly how cold that is. So I want to go from 0 Kelvin, and we're going to have to go to degree C first because we don't have a direct conversion, all the way up to degree F. And because everything we're working with here is an exact number, that 0 is an exact number, for the sake of discussion, let's go ahead and take it to 3 sig figs, just for this problem. All right, so degree C is, what do we have here? Are we adding or subtracting 273? We're subtracting. Yep, so we are going down in the scale, so minus here. In the other problem, we added because we're going the other way. All right, so here, this is pretty straightforward. And my units here are degree C. Okay, so on this part here, you definitely want to be careful of your signs because we have a negative sign here now. Be careful that you're going in the correct direction. So I want to figure out degree F. So in this case, we're going to a larger number, so I want to use the 9 on top. So 9/5. And then we're going to multiply that by negative 273.15. After that calculation, we're going to go ahead and say plus 32 after the multiplication. All right. So now we break out our trusty calculators. And 273.15 times 9/5. All right, so what do we have there? That's 491.67. That number is technically negative. So just for that, -1. And then here, plus 32. And I'm getting negative 459.67. Yeah, let's go ahead and take it to all the digits. It's all exact numbers anyway, so pretty cold. So thankfully on Earth, it'll never be at 0 Kelvin. Pretty cold. Coldest temperature I've ever personally been in is -15. At least that's where my thermometer stopped going. It just kind of stopped. I was like, is it stuck or is that actually the temperature? So then I brought it inside and it actually like warmed up. I was like, okay, it's not stuck, so I put it back outside. You know, it was minus 15. Pretty cold. Go ahead.
So for the equations for Fahrenheit, you multiply the 9 multiplier the 6 degrees Celsius Fahrenheit.
Yes, and then you add the 32.
For Celsius, is that the same, or do you do
For Celsius, if you're figuring out Celsius from Fahrenheit, you subtract first, and then you do the multiplication. All right, guys, we are just about out of time. Remember, you guys are always more than welcome to stop by. This weekend, you got a lot of practice to do. I highly recommend that you practice stuff on paper first before you even open mastering. Because the stuff that we're doing in your practice is not worth points. The stuff on mastering is worth points. So if you want to maximize your points, what do? Do that after you've practiced. All right. Well, have a good weekend. I'll see you guys next week. We have class on Monday, this coming Monday.